All right, so I think we are recording. Okay, thank you everyone for your patience. Greetings to all. So welcome to our first RASEI Big Energy Seminar of 2021. And so today we have the honor of having Professor Carlo Bottasso as our speaker. And as most of you heard, we are recording this seminar, and it will be available and posted to RASEI's website as well as RASEI's YouTube channel. So Carlo is the founding director of the Wind Energy Institute, and he holds the chair of wind energy at the Technical University of Munich in Germany. He received his PhD in aerospace engineering at the Politecnico di Milano in Italy, and he was a professor at the Politecnico di Milano for many years before moving to TUM, the Technical University of Munich, in 2013. So Carlo has many awards and distinctions, and in the interest of time, let me just point out that he has been president of the European Academy of Wind Energy and is one of the editors-in-chief of the Wind Energy Science Journal. So I know we are all in for a treat today as Carlo talks to us about the main scientific questions facing the field of wind energy, and he'll also tell us about some of the work that his institute is doing to address these questions. For the seminar, if anyone has burning questions that they feel needs to be answered right away, Carlo has said you can go ahead and unmute yourself and ask. Otherwise, you can type in questions into the chat box, and I think we'll, for the most part, address questions at the end, unless we feel like that there's a very pressing question. And you can also, raise your hand electronically through the participant list and also the reaction button. For the most part, unless we feel that it's a very pressing question, we'll wait to the end. So thank you everyone for joining today, and let's welcome Carlo. So Carlo, feel free to take it away.
Okay, so thank you, Lucy. Good morning, everybody. For those of you in the US, I understand there are also some people in Europe, so good evening to you, wherever you are. It's really an honor to be here. So I want to thank you, Lucy, for inviting me. It's really a pleasure to be here. And I want to say that it's really a pity I cannot be there in person. So I want to start by wishing everybody that this year will finally bring us back to our normal lives. So I wish you the best of everything for this year. So today I want to speak about innovation, and I will also take the opportunity to make a few points and also to show you some of the things that we do in my group at TUM. And I want to speak about innovation because I think we're living a revolution. So we're living a very important time. We're living a fundamental transition. So the energy system is changing radically under the push of a number of coupled megatrends, including climate change, a better awareness of the value and importance of the environment, but also electrification in all aspects, from transportation to heating to cooling, the importance of data, a growing population, urbanization, and so on and so forth. So this is pushing really a transition in the energy system that is of fundamental importance. And there are predictions that say that we can expect energy from wind to provide between 1/4 to 1/3 of energy across the globe by 2050. So if you think that this is very ambitious, it is very ambitious, but in reality, to some extent, it is already happening. So a highly industrialized country, and a fairly large country like Germany, for example, today already has 26% of electricity coming from wind. Smaller countries like Denmark, for example, early adopters, of course, you can see numbers which are astonishing, like 48%. I think these are the latest figures. So how do we get there? I think there are a number of trends. So one trend that I think is of fundamental importance is moving offshore. So again, for example, if I look at Europe, the European Commission has a vision to have between 230 to 450 gigawatt of offshore wind by 2050. And this is meant to exploit the incredible resources that we have in sites like the North Sea, but also the Baltic Sea, the Atlantic Ocean, and also to some extent the Mediterranean. So it's pushed by, again, a desire to increase the penetration of wind, the availability of sites with fantastic wind resources, but also the need to move away from people to mitigate the impacts and improve acceptance, which in some countries is a problem of fundamental importance. We'll come back to this in a second. By the way, this is also calling for innovation, because although in shallow waters, I think we already see very interesting prices, there is a tendency, of course, to try to also go into deep waters, which is, for example, very important in the North Sea and also elsewhere. So again, if you look at the budget of research in Europe in the coming years, there is a significant amount of money for wind that is going to go towards floating offshore to push that technology. However, offshore is not going to be all of it. Again, these are long-term strategies of the European Commission that is expecting to see, even in 2050, still 60% of wind coming from onshore installations. So this means that onshore is not going away. Actually, onshore is going to play a very important role. And once again, onshore, especially in highly populated areas, once again, Europe, means impacts. And so again, the mitigation of impacts is really becoming a very pressing need. So these are very ambitious plans and targets. And so the question is, what will take us there? What can make this possible? In my opinion, there are two fundamental things: innovation and scientific knowledge. So today we'll talk a bit about a mix of the two. I just want to point out and take the opportunity here to say that I had the privilege recently to work with a number of distinguished colleagues, many of whom are here today. We wrote together a paper that was published in Science, where we identified three main grand challenges that need to be overcome, if you want, in order to achieve these goals. And these main grand challenges deal with the understanding, the modeling, and the simulation of the atmospheric and plant flow, and the turbine and the plant. The work that we do in my institute is mostly related to the second and third topics, so turbine level and plant level. So I'll spend most of the time today to talk about those two things. However, before I jump there, I also want to say a few words about the flow, which I think is of fundamental importance, although is really not my field. I also want to say that the original team is split up in a number of smaller teams, and also we recruited additional people, and we're working on a number of follow-up papers on specific scientific specific topics, and these papers will appear in the Wind Energy Science, which is the open access peer-reviewed paper journal of the European Academy of Wind Energy. So I just want to say, as I said, a few words about the flow, and I want to show you this beautiful collection of movies that I got some time ago, courtesy of Paul Veers, that try to make the point that in reality, this is a fundamental problem of incredible range of scales. We go from the global scale to the regional scale, to the plant level scale, then down to the inflow of the single turbine. And this really is an extreme multi-scale, multidisciplinary challenge. So we need to be able to model and simulate what happens at the boundary layer scale. It means scales in space of millimeters and in time of milliseconds. And then you have to go through the inflow at the rotor, the intra-plant flow, we'll come back to that later on, to the mesoscales, where you look at scales of tens, hundreds, sometimes thousands of kilometers, and time scales of hours, days, sometimes even weeks. So the range is incredible. And this is not only a problem from the aerodynamic point of view, you have a similar situation also from, for example, a structural point of view. So when you look at material behavior and composites, you have, matrix and fiber, you have microcracking, again, very small scale phenomena, both in space and time. And then again, you go to the interaction of a 200-meter rotor with the inflow. So again, this is a fundamental challenge. And I want to say here that this fundamental challenge is even more difficult because it cannot be answered only by looking at super high fidelity first principle methods and models and tools. In reality, we have to design and deploy these machines, and therefore we are engineers in the end, and we have to solve a number of practical problems. And so, for example, design, performance, controls, forecasting, siting, operation and maintenance. In order to support these applications, you need a range of tools that are able to span the scales in space and time, but also spans the application space, which is extremely challenging. Also because some of these applications are extremely demanding, are repetitive tasks where you have to do multiple simulations and many times, for example, because you're optimizing something. So this really raises the bar and makes this really one of the main challenges, I think, around. Now let's turn the attention maybe to the turbine, and then we'll talk a little bit about the plant, because as I say, this is maybe closer to the things that we do. So I just want you to look at this picture to get an idea that we're dealing with the largest rotating machines on Earth. And getting there has been a process that goes back a long time. It started a long time ago in garages in Denmark, which, however, these guys identified, I think, a configuration that is clear as a very important potential. And over time, this has grown and will keep growing over time. And this has been made possible not by simply zooming up or upscaling the initial designs. Really, this path of growth and evolution really has been made possible by fundamental innovation at all levels. So if you talk about the turbine, I tried to list here some of the areas where innovation is important. It's certainly not an exhaustive list, but design and controls technology, aerodynamics, materials, manufacturing, generators technology. Innovation is really present everywhere. I think this is clear to everybody. What I want to highlight here is one important thing, is the importance of assessing the value of innovation. So sometimes it's relatively easy to have an idea, but then in the end, whenever you have an idea, you have something new, you have to realize that you'll have some benefits, but you'll also have some drawbacks. And so in the end, you have to ask yourself, okay, this is a nice idea, but do the benefits really offset the drawbacks? Does it make sense to use this? Does it really pay off? And sometimes answering this question is not obvious. So you can give lots of different examples. I take the opportunity just to show you one example, one recent example taken from a paper from one of my very brilliant PhD candidates in my group. Here we have been looking at LiDAR CC controls. This is nothing new. This is called LUC. So the idea is that you have a LiDAR, there is a sensor that is scanning the wind in front of the rotor and measuring the wind. This is beautiful because you are measuring in front of the rotor. So let's say that you measure 100 meters in front of the rotor and you have a 10 meters per second wind. It means that you're measuring the wind that will hit the rotor 10 seconds from now. So you have a preview of the future. This is fantastic because, by definition, if you think about feedback controls, by definition, feedback controls is always late. When you do feedback controls, you're measuring the response of something, and then you're reacting to that measurement or that response. But if you measure a response, it means that something is already happening. So by definition, you're late. With preview information, you avoid this because you look into the future. So this is certainly a very nice idea. It has been, there are many papers since several years, people looking at various formulations and so on. And it's clear that this is a significant potential for reducing loading. So now that we know that we can reduce loads, then the question is, okay, what do I do with these reduced loads? I can try to improve the design. And so we try to see whether these load reductions really make sense and bring value. And so we said, okay, we can try to use these load reductions in several ways. And for example, these are three, I think, important ways of using those load reductions. I can design a bigger rotor that will have a bigger swept area, and therefore I capture more power, and at the end of the year, more energy, so I make more money. Or I can design a taller tower, so I go higher above the ground, and so I catch more wind. Again, I will, in the end, improve my energy production. Or I can do something else. I can try to design a tower for an extended period of time. So towers typically are quite expensive, are one of the most expensive items in a wind turbine. So I could try to design a tower that, instead of having the lifetime of the turbine, could have a longer lifetime, 30, 40 years. I could start installing a certain rotor on it, and then after 10, 15, 20 years, take it down and put another one. So the tower becomes a component, an expensive one that has a longer lifetime. Again, this is something that could be enabled by luck. And so we studied these three ideas, looking at three very different turbines. So a 10 megawatt class 1A offshore, a 2.2 megawatt class 2A onshore, and a 3.4 megawatt class 3A onshore. And we looked at the potential of luck for redesigning these turbines. So the main findings are written here. So number one, you can try to reduce ultimate loads. The problem is that not all components are driven by ultimate loads, only some of them. And not all driving loads come from conditions that can be influenced by luck. So for example, in many turbines, some extreme loads come from conditions where the machine is not even controlled. For example, it's idling or parked. So in that case, even if you reduce a load in operation, the driving load is another one that you cannot change by luck. And so basically luck doesn't really do anything. So it doesn't bring you any value. In addition, if you design now a turbine with reduced ultimate loads thanks to luck, then you have to be super sure that luck will always be able to catch the condition that is causing those loads. So this might mean that you have to have multiple lidars, and you have to ensure availability, and so on and so forth. So it's not easy, let's say, to improve the design by looking at ultimate loads using luck. The story is different if you look at fatigue. In that case, it's easy to show that luck has a very significant beneficial effect on fatigue loading. But here again, it's not a free lunch, because number one, not all components are driven by fatigue, only some of them. And number two, even if you have a benefit from the fatigue point of view, you still have to buy your lidar, maybe more than one, over the lifetime of the turbine. You have to maintain and repair the lidar, and this comes to a cost. So when you bring everything together, turns out that most of these ideas of trying to redesign the turbine do not really pay off. So for example, here we're looking at the larger rotor design for the 3 turbines. And if you look at the cost of energy, in reality, it increases. Even if we account for uncertainties, of course, this is very uncertain. So we have a band of performance that we're taking into account. But in reality, this doesn't seem to pay off. And it's the same is true for a taller tower. So the only solution where we saw some benefit is this idea of designing for a longer lifetime, especially in the case of the 10 megawatt turbine, where the tower is massive and costs a lot of money. So again, it's not the point here to go into the details of this specific study, but the point that I want to make is that, once again, real innovation is not just a new cool idea. And if you want to understand whether your new cool idea really pays off, you have to take a system level point of view. So from this point of view, I think design is really the queen of all disciplines, where you bring all together and you can evaluate pros and cons and find trade-offs and really understand what works and what doesn't. I also want to make here another point. Innovation should not be meant only to improve performance. In reality, as I said, I think especially onshore, especially in some countries, and Germany, I think, is maybe one of the #1 examples here, impacts are dramatically important. There are places where there is a lot of opposition to wind energy, and the only way to reduce this is by showing that we can mitigate the impacts. In reality, of course, we have impacts. I mean, every technology will always have impacts. And of course, wind energy also has impacts. I try to list here at least some of the impacts in the onshore case. from noise to impacts on the wildlife, visual impact, also things that go maybe sometimes beyond engineering. So perception, aesthetics, heritage preservation, very important in the south of Germany, for example, but also low frequency vibrations, effects on the microclimate, crops, but also energy consumption and emissions during manufacturing of the turbine, and also end of life. I mean, today we're still able to recycle very little of our wind turbines. Most of the blades end up in landfills. So repurpose, recycling, all these things are becoming of great importance. So even here, I just want to give one example. Of course, this is a huge topic and a lot of people are working on these things. I just want to show one recent work that we did in my group. So we tried to say, okay, instead of designing as usual a turbine looking mostly at LCOE or other metrics, but still related to purely economic metrics, can we do a eco-conscious design of the turbine where we take into account the whole life cycle of the turbine? So of course we still take into account LCOE, energy production, operation costs, and everything, but we also want to look at other aspects. So specifically we have been evaluating the impact in terms of greenhouse gas emissions expressed in terms of tons of CO2 equivalents. And if you start digging into this, you can see some interesting things. So you can break down the impact of energy in terms of these greenhouse gas emissions during the various stages of the life of the turbine. For example, material extraction, manufacturing, operation, end of life. For example, end of life, here you have a negative budget in the sense that we can recycle something. This is mostly coming from the steel in the tower today, nothing more. And then in the end, we can evaluate the total impact. You can also break it down by components and materials. This is also very interesting. It shows that the tower is the number one component we have to target, but then the nacelle, the blades are also very important. And there is not only the point of view of the turbine, you also have the point of view of the grid. So this is data from Germany. It shows the greenhouse gas emissions as functions of wind speed. And this shows something very interesting, although obvious. You have higher emissions for low wind speeds, of course, because you have more maybe coal or oil or other fossil-based sources. And the more wind speed more wind you have, the less the greenhouse gas emissions. So this also shows that you have to design turbines that are able to produce at low wind speeds from this point of view. So this will push the design towards low specific powers, which is the same that happens if you look also at the cost of energy. The cost of energy spot market price is also typically has an inverse relationship with wind speed. So both trends will push you in this direction. Again, means bigger and bigger turbines with low specific powers. So we take this, we throw this into our design environment, which would be maybe similar to what you have in the US, like Wisdom. So this is something that is able to change the blade shape, diameter, rotor tower height, sizing, all the various structural components, running all the various DLCs and taking into account all the classical, things that you need to take into account when you design a wind turbine according to the standards, the design standards. So we throw this to this environment, and we solve a multi-objective optimization problem now, where we looking into cost of energy, but also this environmental impact. We can also take into account opportunities coming from other technologies to reduce the emissions. For example, hybrid towers where you have less steel, more concrete, generator technology, materials like helium, for example, or similar thermoplastics where you can improve the recyclability. And in the end, you get something like this. So you get a Pareto front of optimal solutions. So it's a family of solutions where you're trading essentially this impact of energy versus cost of energy. And it's kind of interesting because, again, I'm not really interested in showing what is, what these turbines look like, but I think it's interesting to see that basically if you pick solution is moving down in this direction, then you're improving the value for society because you're reducing the emissions. If you move in the opposite direction, you improve the value for the individual, for the customer, because you're reducing the cost of energy. So again, this brings me to another sort of take-home point that I want to make. I mean, what is value? Value has many different meanings. It has different meanings for different stakeholders. If you take the point of view of the society or the final consumer, you might end up with different solutions. But in reality, this also shows that we have to be careful, and there is much beyond LCOE. And I really think that we have to think a bit more in the direction of this value. What is value? And I think we can discover lots of interesting things if we can keep exploring in this direction. Let me move now to the plant level. This is also a very fascinating topic because the plant is not simply a collection of wind turbines. The turbines are coupled together by the wakes. Behind the wind turbine, you have lower wind speed, so you have a speed deficit. It means you produce less, but you also suffer for increased loading due to the higher turbulence. So this really brings the level of complexity to another level, because you have a coupling through turbulent beasts, these wakes. And so you have to understand how they behave, how they change their properties depending on ambient conditions, depending on the design of the turbine, depending on how you operate the turbine. So this is again another huge area where innovation can make a really big difference. So I listed here again not an exhaustive list of topics that I think are important: wake physics, plant controls, which means how you coordinate these turbines together so that you improve the performance not at a single unit level, but at the level of the whole plant. How you measure what is going on, how you design the plant, how do you use data, how do you connect to the rest of the grid. So there are lots of aspects. Clearly, we cannot cover everything. I just want to make a few points. And a point that I like to make is about plant controls. Plant controls is a fascinating topic where you essentially learn how to make these wind turbines not individualistic, but let's say, able to cooperate. So there are many different ways of doing plant controls. We don't have certainly the time here to go into the details, but simply maybe I want to mention here that one of the most promising ideas is what we call wake steering. The idea of wake steering is that instead of pointing the rotor into the wind, you slightly misalign the rotor with respect to the wind. And if you do this, what happens is that you're able to move your wake sideways. So if you know what you're doing, you can reduce the interaction with the downstream turbine. So this, by the way, this goes back to what we said before. It's a trade-off analysis once again, because as you point the rotor away from the wind, you lose something, you lose some power, you increase some loading, but you gain something else. You gain power, you reduce loading downstream. So the question is, what you gain behind more than what you lose in front? And the answer is typically yes. If you do it right, you can have a net positive effect. So this is extremely interesting, extremely promising. A lot of people are working on this. I just want to make the point that this is really at the forefront of controls. In reality, look at this movie here. These are the Boston Dynamics robotic dogs. What are they doing here? These are autonomous robots who are able to cooperate. So for example, here we can see a robot that is opening the door to the other robot. I don't know, why isn't it supposed to show? Okay, you see that they're cooperating. So one dog is opening the door to the other robot. Isn't it the same that we have here? I mean, we have one turbine that is opening the door to the next turbine, if you want, and moving the wake aside in order to improve or let the second turbine to operate in a better way. So here the keywords are that wind turbines are in reality robots. They are autonomous machines that work with no supervision in a very difficult environment that is changing all the time. So this should give you an idea of the complexity of this problem. Clearly, the payoffs are very important, because if we learn how to do this well, I think we can have a lot of benefits at various levels. So again, we can, I don't want to talk about the specifics of wind farm control. I think you have lots of experts also in the US. A lot of these ideas are also coming from people in the US. So I think it's not the point here to recall all this. I just want to make a point on validation. So in the end, we need to prove to industry that this works. And this is, of course, the final goal. And this is indeed also what we are doing. So these days, we're actually running a wake steering experiment in a site called Kirkmuso with some colleagues in Germany. And it's based on the idea of wake steering. So this is the wind farm that we're using just these days for these experiments. However, I want to say here that field testing, it is indispensable, but it's not an easy task. It costs money. Whenever you do field testing, you will have some power losses, probably energy losses that you'll have to compensate. And so some people will have to be reimbursed for this. You have liability issues. You have IP issues very often. Even if you work with companies, you don't have full access to all the information that is relevant to your experiment. And in addition to this, you have no controls on the environment. So the wind is what it is, and you only know it partially. So even if you have maybe a met mast, as we have in this site, even if you have LiDARs, very often you have a partial understanding of the conditions at the site. So this is certainly indispensable, but I just want to make the point that there are alternatives and there is value in smaller scale experiments. I think there is somebody who I hear a lot of background noise. If you could please mute your microphones. Thank you. I just want to show here these experiments that we're running with my group in collaboration with colleagues in Milano. Over the years, we have developed the ability to design small-scale wind turbines. There are real wind turbines in the sense that they have individual pitch control, torque control, and yaw control. And they are optionally also managed by a supervisory controller, so wind farm level controller. And in these experiments, the beauty of these experiments is that we have full knowledge of the conditions. We can generate wind speeds of different speed, turbulence intensity, vertical shear. As you saw, we can also simulate variable wind directions by moving this turntable. And we can go and measure with very low cost and relatively good accuracy all that is happening. So this is really giving us a number of opportunities to validate the ideas, validate the simulation tools, and also answer some questions that I think are difficult to answer at full scale. So for example, this is just to show that with the measurements that you get in the wind tunnel, we can validate, and we did a significant validation campaign of LES coupled with the actuator line model. Now everybody is using LES and actuator lines to simulate turbulent flows and wind turbine flows and wakes, but the validation of this remains difficult at full scale. Here we can, for example, we studied this three wake interaction, including wake steering. And again, we can go and we measure with a LiDAR or without wire probes the wakes, and we can perform a full digital copy of the experiment using LES, including the wind tunnel, the process of generating the turbulent flow, everything. And we can go and check and show that we indeed have good accuracy, even in these complicated wake interaction conditions. So to me, this is something that has a very important value also to add to the credibility of the tools that we're using in a number of applications today. Again, without going to the details, but I think there's also some interesting questions. For example, all these controllers are based on models of the flow. And so they're model-based in a sense. So the question is, do you really need a very accurate model, or can you do also with a rough model? And we deal with uncertainties everywhere. So the flow is uncertain, the wind direction is uncertain, where the turbine is pointing is also uncertain. So we typically use robust formulations that try to hedge against these uncertainties. So we can also answer the question, are these uncertainties, are these robust formulations really important? Now, I probably don't have the time to go into the detailed explanation of these diagrams, but I think since we know in this case what is the ground truth, we can answer these questions by these experiments, something that can only be done in part, in my opinion, at full scale. Another important topic is machine learning. Now everybody's jumping, of course, on machine learning, data, using data to improve models and so on. But the question is, when you're learning something, are you sure that you're learning the right things, or are you only doing data fitting? Can you prove that you learn the right things? In order to be able to do that, you have to have good knowledge of the ground truth. So for example, here we were trying to learn secondary steering. Secondary steering is a phenomenon that takes place essentially when you steer a wake. So as in this case, when you steer a wake, you create also a lateral flow outside of the wake. And this lateral flow will change the inflow at the downstream turbine. So this turns or changes the direction of the inflow at the downstream turbine. This is called secondary steering. Now we use data to learn secondary steering. But now, since again, we can measure everything, so we know the ground truth, we can prove that we're not simply data fitting, but we are learning the right correction or the right phenomenon. So again, to summarize, I think a take-home point is the field is the final judge. I'm not questioning that. It's obvious. We have to go to the field. The field remains extremely important. But in my opinion, there is value in controllable, repeatable, scalable experiments that have the right degree of sophistication. So you have to do things in the right way, but if you do things in the right way, you have scaled experiments that are very, very interesting and very realistic. And then I want to leave you with a final example, a final point here, is the point of situation awareness. So I want to show you this movie. This movie is what your Tesla autopilot sees when you drive your Tesla down the streets of Boulder, for example. Look at this. I mean, it knows a lot of stuff. And this is on the fly, so it's able to recognize the environment on the fly, and the ability to drive the car in an environment that is unknown a priori and changing all the time is built on this situation awareness that comes from the use of a number of sensors. Okay, so situation awareness, in my opinion, is the key element of most advanced control applications today. What is the situation with wind turbines? In my opinion, we're lagging behind a little bit here because a wind turbine today is equipped with a sensor in a nacelle, which is an anemometer and a wind vane that will only give you nothing else than a velocity vector at a point. So speed and direction, nothing else. So from a point-wise measurement, you know nothing about vertical shear. You know nothing whether there is a wake that is impinging on your turbine or not. So in reality, we're saying that we're doing sophisticated robotic applications in changing environments, but having no clue of what is going on. So, or very limited, let's say, I'm exaggerating, of course, very little clue of what is going on. So my question here is, can we do better? And I think we can do better. And so we have been trying to push the idea in the last few years in my group of developing what we call wind sensing, which is a pretty general idea. It's the idea that you have data anyway. You have power, you have very often loads. Many modern turbines already mount load sensors because they do IPCs or integral pitch control for load reduction, or maybe monitoring, health monitoring, these kind of things. So you already have a lot of data. The question is, can we use this data and essentially measure the response of the turbines and estimate what are the inflow conditions of the turbines? So can we estimate the vertical shear? Can we estimate and see whether there is a wake impinging on the turbine? If the answer is yes, I think we can use this information in many different ways for wind farm control, but also for lifetime estimation. I think you name it. It's clear that if you have this information, you can find good ways of using it. Of course, LiDARs will come. Of course, LiDARs will give us all the information that we want in the future. But in reality, I think we can do a lot today for free. Because again, if you have this data already, if you have these load sensors installed already, this is a software update. So you don't need to put any additional piece of hardware. It's simply using the information that you already have in a clever way. And I want to give you two examples. So this is a test site in north of Germany called Brussow, where we have 2 wind turbines, 3.3 diameters away. We also have a met mast, and these turbines come equipped with load sensors. And so here we want to show the ability of measuring the presence of the wake, so the impingement of a wake from the front turbine to the back turbine. So the way we do it, again, I don't have the time to go into the details, but essentially we use the blades as local sensors. The blade, as it moves over the rotor disc, scans the rotor disc and feels changes in local wind speed. So it's essentially a correlation between wind speed and loads. And now what we do, we also take a sort of average. And so we look at 2 quadrants. So let's say left and right, and then we can estimate the average wind speed on these 2 quadrants. And by doing this, we can try to track the presence of a wake. So for example, here in this movie, let me restart it. Hopefully it will restart. Okay, in this movie, that is not restarting. Okay, now it is restarting. You see the direction of the wind that is changing. The total wind speed with respect to the one measured by the mast is also changing. So here you're measuring the wind speed downstream, so you feel the presence of the wake when the wind is blowing, in the direction of the 2 turbines. But here you see the red and blue sectors, and by looking at this difference, you can fit your wake. And so here you have a wake detector. Again, a wake detector that requires no extra sensors in addition to the ones that you already have. And so this is able to tell you the wake is impinging on the right or the wake is impinging on the left. And this is useful for wind farm control. Another application is estimating wind shear. So again, vertical shear is not something that you can measure from a single anemometer in the nacelle. Here the idea is similar. So we use the wind speed, in this case, over 3 sectors. And from here, we measure the vertical shear and we compare it to the shear that we measure at the met mast. We do it only with 3 sectors because the met mast is only tall up to hub height. So it doesn't reach all the way to the tip of the rotor. So here you see a comparison in black of the shear measured by the met mast and in blue by the one observed by the observer. It's not perfect, but it's picking the trends. And so you might ask me, but why do I care about shear? And I think there are quite some reasons why you might want to care about shear. For example, this is, again, an LES simulation, where we generated 2 flows, one stable and sheared, and one unstable and with much less shear, that have, however, the exact same wind speed and turbulence intensity at hub height. So a wind turbine operating based on current technology would not be able to distinguish between these 2 operating conditions. In reality, although the conditions at hub height are apparently the same, in one case it's stable, the other one is unstable. So of course the wakes behave in a very different way. So if you look at, again, hub height, if you look more in 3D, the differences are even higher. But even at hub height, where the conditions appear to be the same, the wakes are very different. So look at the red and blue curve. So although the gap or the speed deficit appears to be the same, the shape of the wake, so the way the boundaries of the wake, how much this diffusion zone where you have mixing is very different in stable and unstable conditions. So I think this is also where like a warning. I think most of today's wake models that we use for wind farm control only look at turbulence intensity as a proxy of stability. In reality, that's not necessarily the only indicator. We should also probably also use some other indicator, and I think vertical shear is certainly a good candidate. So I will stop here. I just want to make a couple of very quick comments. I think the future looks bright. Wind energy will play a fundamental role in this revolution that we're living, and we're lucky to live in these interesting times. As scientists, I think we're certainly not out of work. There are lots of interesting things we can do. So it's not business as usual. It's not simply deploying the turbines in the field. It is innovating. So there is a fundamental role of research and innovation. I want to stress the fact that this is not a collection of knowledge already available somewhere else that we put together. We really need a dedicated body of science, and this, I think, is emerging clearly today. Everything will work and keep working if we have a healthy collaboration between industry and academia. This is of fundamental importance. Only working together we can make progress on all fronts. And then finally, education. Education is of fundamental importance. We need people with the right skills, with the right background. And so this is becoming more and more available. Up until a few years ago, you saw only very few courses dedicated to wind energy in universities worldwide. Now the situation is changing. But this is, again, of great importance, so we need to go in that direction. The final slide is dedicated to a very large number of collaborators. Of course, whatever I've shown you is based on the work of a number of very dedicated people, very bright, brilliant people. I listed here some of the latest PhD students in my group, and all the acknowledgements have to go to them. So I want to thank again for your attention. I will finish here maybe a couple of minutes late, but ready for questions. So thank you very much.
Thank you, Carlo. That was perfect. And we actually started a little late with the recording difficulties, so I think it was perfect. So we'd like to open it up for questions. If anyone has questions, I think you can raise your hand or unmute yourself and ask questions. I see Julie has a question, so go ahead, Julie.
Hi, Carlo. Thank you for that wonderful and exciting and invigorating and inspiring overview.
Hi, Julie. Thank you.
Thank you so much. I was really excited to see you mention the importance of considering atmospheric variability, and in particular looking at wind shear, using the blades to sample that. And I was wondering if you had opinions about what other atmospheric characteristics we should be also looking at, like wind direction veer, or looking at turbulent kinetic energy instead of just the horizontal component of turbulence intensity. Do you have any perspectives on where we should be looking next?
Absolutely. I think we need to be a bit more careful about atmospheric stability. So again, atmospheric stability cannot be characterized, even from a theoretical point of view, simply by looking at turbulence intensity. So as far as I understand, we need at least two parameters, vertical shear, turbulence intensity. So I think we need to make some advancements here, because it seems to me that most of today's wake models do not really take this into account. I'm talking about the engineering wake models that we use for synthesizing the control loads. Clearly, the LES doesn't have this problem. You mentioned veer. Veer is extremely important, extremely interesting. We have been trying to estimate also veer. To be honest, I have to report that up to date, we haven't been able really to estimate veer credibly. That is our next step. So the question is, can you distinguish veer from wind direction in a way that is reliable? No, but I think that would be certainly useful. Kinetic energy also, as you mentioned, that's also another one. Another question that I have, and it's maybe a question more for people like you, are more into the fluid dynamics. I mean, turbulence intensity, you can measure it in many different ways. So if I measure turbulence intensity at one point with an anemometer, or if I measure it over the rotor disk, I get very different values. Which is the right one? Is there a right one? Are these different values telling us anything interesting? So I think that's also something that I would like to understand a bit more. So sorry, I don't have very good questions to your, very good answers to your questions. I have questions than answers.
No, that's great. I think emphasizing that more research is required and lots of new things to understand. That's fantastic. But thank you.
Yeah, definitely. Thank you. Thanks, Julie. So a number of people have commented an outstanding presentation in the chat. There's a question from Joachim Weber at NREL. Says, Carlo, fantastic, beautiful talk with eagle perspective. Thank you. Given the holistic and fundamental approach to innovation in order to live up to the megatrends and drive the transformations to achieve the required positive impact and value, all fully agreed, what is your perspective on the role of airborne wind energy technology as an equally fundamental additional technology paradigm in suitable applications markets?
That's a good question. To be honest, I would love to see airborne take off. I'm an aerospace engineer. I was a professor of flight mechanics at the Polytechnic in Milan. I've been teaching flight mechanics for half of my life before turning to wind. So that my heart goes there. Having said this, you know, it's difficult. It's in the end, we also have to have an economic case, let's say. It's not only for the sake of it, we have to show that it has its own niche. And that's not clear. Also, for example, the recent indication of Makani/Google pulling out of this seems to indicate that it's not so clear that there is a market there. So this also goes beyond my real understanding. I think it has a niche, but in reality, you have to show that you are capable of selling these turbines in the market in the end. So I hope somebody will make some progress there. I would really love to see developing further. There are some companies in Germany that are trying hard in this direction. So I wish them luck.
Great, thank you.
Great, wonderful. So that I have a question kind of following on that. You know, you had talked about, you know, levelized cost of energy is not necessarily, you know, being maybe the best metric to be using. Do you have suggestions for alternatives?
I'm not saying it's not the best. I'm saying there are many possible metrics. So there are many ways of looking at the problem. I think there was too much emphasis in the past only looking at LCOE. I think a lot of people are recognizing that there are other ways of looking at this. I think Catherine is probably also in the audience, has been looking at other values. However, again, what I wanted to say is that the economic value can be measured in various ways, but you can also try to go beyond the pure economic aspect, and you're embracing also other aspects, in my opinion, are equally important. And actually, I think as engineers, we should try to show that we also care about these other aspects. So it's not only about delivering the energy at the lowest cost, it's in a way that there is a minimum possible impact. Because in reality, we have to recognize that, you know, what we're doing has some impact, as everything has impact. And I really believe that this story about innovation and value and so on should look a bit in a broader sense to this problem. So beyond economics, let's say.
Right. Okay, great, thank you. Are there any other questions or comments? So Paul Fleming has a question. Go ahead, Paul.
Yeah, thanks. Thanks for a very, very nice talk, Carlo. A lot to think about. My question is just, I'm very curious about the field campaign you mentioned in wake steering, and I was wondering, is it published somewhere? Will it be published? Is it going to be public?
It will be published. Yes, it is ongoing. So we'll publish it. We are looking at the data now. We still have a few months to go, but it will certainly be published. It's a German project funded also by taxpayers' money, so everything will be published open access. Absolutely.
Really look forward to that. And thank you.
Okay. Sure.
Great. And Paul Fierce has a question in the chat. Paul, if you want to go ahead and ask directly, feel free to.
Sure. I appreciate your attention to design as the queen of disciplines. And I just want to know what you think about the opportunity for customization, given that we may have turbines within wakes, turbines that are outside of wakes, different locational constraints, even environmental constraints. What do you think the opportunity is there for customization of the plant and the turbines within the plant?
I think to some extent we already have some customization that is possible. Very often companies now offer various options in terms of tower height, rotor size, kinds of blades, add-ons, control settings. So we have already quite a degree of customization that is possible. I think as we become better in all these aspects, so design becomes faster, manufacturing also maybe improves and so on. I think this will open up opportunities for even more customization, which in the end means also optimization.
All right, thank you very much.
Thank you, Paul. Nice to see you.
So Paul Fleming has another question. Go ahead, Paul.
Sorry, this one, let's say a bit more open-ended. I'm just very curious your opinion of this. As like there's rumors of impending like more and more commercial products in the wake steering space. How do you see that changing the research and innovation field of people connected to that space?
Well, I think it's good that products are coming out. It means that industry realizes that this works. However, I mean, this probably doesn't mean that there is nothing else to do. So wake steering has potential, but I see also a lot of other things that can be added on to improve it. So, for example, these ideas of mixing. These ideas of maybe designing rotors that are able to enhance recovery of the wake, co-designing everything. So I think there is still a lot of space, and there is still a lot to understand and improve. So I'm not scared by the fact that industry is coming out with products. Actually, I think I see this as a good news in the sense that we're doing things that are relevant, and industry is paying attention.
Yeah, I agree. And thanks for sharing your thoughts on it. It's something I'm thinking about these days. So nice to hear what you think. Thank you.
Thank you, Paul.
Great, thanks. And then we have Gary Rumbles has a question. So I'll read it. So, or Gary, I don't know if you want to go ahead and ask it yourself.
Yeah, this is a naive question, and I fear for doing it in front of the who's who of wind energy on this call. But 450 gigawatts of power being withdrawn from the lower atmosphere is quite a substantial amount. And I was just wondering if there are any studies of environmental impacts of withdrawing so much power. I'm a sailor, that worries me.
No, there are studies. I think this is also another aspect that we need to look at very carefully. So as I said, I mean, we cannot have zero impact. We cannot make these turbines disappear, invisible. In the end, we're sucking out energy from the flow. So this has an impact. In Germany, people look at the effects of humidity and in turn on the effects of crops, microclimate, lots of things. I think we have to pay more attention to this. I think only if we pay enough attention to this, then we'll achieve those goals. So it's not only about technology. Technology can also help mitigate these impacts.
I'm just, once upon a time, people burnt coal and didn't think that they had to worry about it. And at some stage, it became obvious that we did. And I was just worried with the wind power and the same with solar power. At some point, there's an impact, and we need to study them before it happens rather than wait until it does happen.
I totally agree. It's not my field, but I know that studies have been done already and some are ongoing. I think we also have here somebody in the audience who can probably also give you a better answer than myself, but certainly people are paying attention to this.
Yeah, I think that's actually a really good question, Gary. I think Carlo might be referring to Julie Lundquist, and we can maybe
exactly
at some point. But yeah, these are great questions. All right, so I think in the interest of time, since we're after the hour, and I know many people have to go on to next meetings or classes, I would just want to thank everyone again for attending, and thank Carlo for just a wonderful, wonderful seminar.
Thank you very much. It has been really a pleasure and an honor. And again, best wishes to all, and stay healthy. I hope to see you in person soon.